Britain built a submarine barely 50 feet long. It was designed to place 2 tons of explosives beneath battleships. Its hull survival margin was measured under 10%. Oxygen inside could fall below safe limits in 90 minutes. Failure meant mechanical breakdown inside enemy harbors. Escape depended on battery reserve calculations. Navigation relied on dead reckoning under tidal drift. A single timer malfunction could destroy the crew. The tow line failure could flood the hull before arrival. Every mission required exact positioning within inches. The X-Craft was not built for endurance. It was built to survive just long enough. Admiralty requirement issued during early 1942. Objective: specified destruction inside defended anchorages. Conventional submarines deemed tactically unsuitable. Harbor nets prevented full hull penetration. Shallow waters restricted deep draft vessels. Design brief demanded minimal displacement platform. Vickers-Armstrong received confidential directive. Overall length fixed near 51 feet. Beam restricted below 6 feet. Pressure hull diameter limited internal volume. Surface displacement calculated under 30 tons. Submerged displacement increased marginally. Hull plating used high tensile steel. Frame spacing reduced stress concentration. Calculated collapse depth exceeded 300 feet. Operational limit set significantly lower. Crew complement restricted to 4 operators. Forward compartment housed commanding officer. Navigation station positioned directly aft. Engineering controls located amidships. Diver compartment integrated behind control room. Diesel engine rated approximately 40 horsepower. Electric motor delivered lower submerged output. Battery banks installed beneath deck plates. Lead acid cells arranged in dual rows. Total cell count determined endurance ceiling. Surface range estimated 500 nautical miles. Submerged range limited by amperage consumption. Fuel tanks integrated along hull sides. Fuel capacity constrained strategic planning. Ballast tanks installed fore and aft. Trim tanks adjusted longitudinal balance. Compressed air cylinders supported emergency surfacing. Single propeller transmitted limited thrust. Propeller diameter constrained by clearance. Hydroplanes mounted forward and aft. Control linkages operated through manual rods. Rudder size restricted turning agility. Periscope mast shortened to reduce silhouette. Optical head diameter minimized reflection risk. Internal walkway permitted single file movement. Crew rotation required coordinated timing. Ventilation powered by low-capacity fans. Carbon dioxide scrubbers used soda lime canisters. Oxygen candles stored near engine bulkhead. Freshwater storage minimal by necessity. Ration allocation limited operational duration. Sanitary arrangement consisted of sealed container. External torpedo tubes intentionally omitted. Primary weapon consisted of saddle charges. 2 charges mounted port and starboard. Each charge weighed roughly 2 tons. Explosive compound primarily amytal mixture. Charge casing reinforced against hydrodynamic stress. Release clamps operated through hydraulic linkage. Clamp corrosion observed during salt exposure. Grease application reduced seizure incidents. Detonation relied on clockwork timers. Timer accuracy measured before deployment. Fuse delay selectable in hourly increments. Timer malfunction probability documented statistically. Premature detonation risk calculated conservatively. Blast radius estimated over 100 feet. Overpressure values compared against hull yield. Safety margin measured below 10%. Hull survival dependent on exact placement. Diver lockout chamber positioned midships. Chamber volume limited 2 occupants maximum. Flood sequence required manual valve operation. Equalization time averaged 3 minutes. Extended flooding increased hypothermia probability. Seal surfaces machined to tight tolerance. Repeated cycling degraded gasket integrity. Leak frequency increased after 10 cycles. Electrical systems insulated against immersion. Cable routing confined within narrow conduits. Condensation accumulated during cold operations. Moisture affected relay reliability. Initial prototypes designated X3 and X4. Dock trials revealed engine overheating. Cooling intake diameter increased subsequently. Engine vibration transmitted through mountings. Resonance interfered with gyro stability. Gyro drift measured 2 degrees hourly. Magnetic compass installed for redundancy. Dead reckoning required constant correction. Echo sounder installation proved unreliable. Chart table surface measured under 2 feet. Navigation plotting restricted by limited space. Tow operations required fleet submarines. Tow line tension exceeded projected load. Tow line snap incidents occurred repeatedly. Hull roll followed sudden release. Ballast shift created temporary instability. Internal equipment dislodged during shock. Battery leakage followed severe motion. Shock absorbers fitted beneath cell trays. Hull plating thickness varied by section. Forward plating reinforced for impact resistance. Weld seams inspected through radiography. Substandard welds removed and replaced. Production secrecy limited available labor. Component standardization reduced assembly variance. Electrical harnesses fabricated by subcontractors. Quality audits logged insulation failures. Seal material shortages delayed completion schedules. Anti-fouling coatings applied externally. Corrosion detected after prolonged immersion. Sacrificial anodes attached to hull exterior. Propeller shaft alignment required precision machining. Misalignment increased vibration amplitude. Motor brushes degraded under sustained load. A battery plate warping recorded post-mission. Internal temperature rose during extended submergence. Heat accumulation reduced scrubber efficiency. Carbon dioxide concentration monitored periodically. Toxic threshold calculated at 5% volume. Exposure beyond threshold caused rapid impairment. Oxygen depletion, window measured under 90 minutes. Unconsciousness estimated within 10 minutes thereafter. Emergency ventilation drills conducted ashore. Diver egress timing recorded precisely. Average external task duration limited strictly. Silt seabed complicated charge stabilization. Tidal currents altered final placement accuracy. Standoff distance required measurement within inches. Incorrect distance reduced destructive effectiveness. Incorrect proximity endangered pressure hull. Fuse winding performed immediately before deployment. Manual winding errors documented during trials. Magnetic signature reduction evaluated experimentally. Degaussing equipment deemed impractical internally. Acoustic profile tested at low speed. Noise output minimized under electric propulsion. Diesel exhaust vented through retractable mast. Exhaust valve fouling reduced airflow efficiency. Surface recharge exposed craft to detection. Weather window selection critical for departure. Minefield intelligence incomplete in several harbors. Keel abrasion occurred during shallow transit. Protective strips installed along underside. Ballast venting produced surface bubbles. Bubble suppression trials yielded limited success. Crew selection prioritized technical competence. Medical screening excluded claustrophobic candidates. Training included confined endurance exercises. Emergency scuttle charges installed forward. Scuttle activation disabled sensitive equipment. Rescue contingencies considered improbable. Operational planning assumed attrition probability. Replacement hulls constructed incrementally. Dockyard capacity restricted production numbers. Maintenance crews rotated among assigned vessels. Inspection intervals shortened after failures. Water pumps manually operated by engineer. Pump capacity insufficient for major breach. Fire suppression relied on portable extinguishers. Diesel contamination reduced combustion efficiency. Fuel filtration units upgraded accordingly. Electrical insulation standards tightened gradually. Shock from nearby explosions damaged fittings. Bulkhead integrity inspected after each trial. Structural fatigue analysis conducted periodically. Battery isolation switches clearly marked. Circuit breakers reset after overload events. Internal communication relied solely on voice. Noise discipline enforced during penetration phase. Harbor nets required diver cutting tools. Hydraulic cutters stored within lockout chamber. Tool maintenance required freshwater rinsing. Clamp release followed fixed mechanical sequence. Incorrect sequence risked asymmetric detachment. Operational depth constrained by hull margin. Pressure tests exceeded normal operating limits. Strain gauges recorded hull stress distribution. Distortion values compared against tolerance charts. Prototype rejection occurred after stress anomalies. Admiralty review boards evaluated performance data. Budget allocations faced internal opposition. Senior officers questioned survivability margins. Engineering staff defended design calculations. Program continuation approved with reservations. Tow depth adjusted to reduce hydrodynamic seismic drag. Surface visibility limited departure timing. Gyro alignment calibrated before final launch. Calibration drift rechecked after vibration exposure. Navigation error compounded over extended transit. Battery consumption logged hourly during approach. Amperage draw compared with mission estimates. Unexpected drain shortened endurance reserve. Emergency recharge required surface interval. Fuel line couplings degraded under stress cycles. Stronger alloy couplings fabricated subsequently. Seal redesign reduced persistent leakage. Moisture traps installed near wiring junctions. Electrical short incidents decreased thereafter. Lockout hatch diameter restricted equipment transfer. Breathing apparatus compactly stored. Apparatus malfunction probability assessed routinely. Scrubber replacement schedule enforced strictly. Scrubber exhaustion shortened safe submergence. Internal lighting powered by low voltage circuits. Bulb failure impaired gauge visibility. Spare bulb secured near control console. Motor torque limited rapid evasive maneuvers. Turning radius remained comparatively broad. Harbor geometry required careful plotting. Escort submarine coordination demanded precise timing. Tow release initiated beyond patrol perimeter. Independent transit commenced under battery propulsion. Periscope exposure minimized during final approach. Harbor lighting reduced visual concealment. Anchor chains presented collision hazard. Soundings confirmed marginal underkeel clearance. Hull contact risked structural compromise. Charge placement beneath keel required accuracy. Fuse delay selected to permit withdrawal. Withdrawal route relied on memorized bearings. Gyro deviation, margin remained narrow. Battery reserve calculated for escape transit. Unexpected resistance increased amperage draw. Power depletion risked immobilization. Immobilized craft faced immediate capture. Capture prevention required scuttle activation. Operational debriefs cataloged mechanical faults. Failure rates exceeded original projections. Incremental redesign reduced recurrence frequency. Production batches incorporated revised components. Dock trials repeated before redeployment. Sea trials followed standardized pattern. Performance metrics compared across hull numbers. Statistical analysis guided engineering adjustments. Explosive shock simulations refined blast assumptions. Measured overpressure stressed structural plating. Hull deformation recorded within acceptable range. Engine restart rehearsed after simulated stall. Battery recharge cycles timed precisely. Air purification cartridges replaced before deployment. Condensation wiped from instrument surfaces. Crew fatigue monitored during endurance trials. Mission duration rarely exceeded projected window. Design compromises remained inherent to platform. Compact propulsion restricted redundancy options. Mechanical simplicity favored space conservation. Redundancy sacrificed to maintain displacement limits. Operational doctrine adapted to mechanical constraints. Harbor strike capability depended on precision. Navigation accuracy determined charge effectiveness. Mechanical reliability governed survival probability. Engineering tolerances defined tactical envelope. X-craft served specialized assault requirement. Production scaled cautiously due to risk. Training accidents documented in confidential reports. Battery fires occurred during charging incidents. Improved ventilation reduced recurrence probability. Hull seam seepage required repeated sealing. Timer misfire incidents triggered investigation. Revised inspection checklist implemented fleet-wide. Diver blackout cases recorded during drills. Exposure time limits shortened accordingly. Tow vibration cracked external fittings. Reinforcement brackets welded subsequently. Control rod stiffness increased under pressure. Lubrication schedules adjusted for reliability. Hydroplane feedback linkage recalibrated precisely. Rudder cables inspected before each sortie. Fuel gauge accuracy verified manually. Engine shutdown drills practiced under load. Charge casing hydrodynamics affected stability. Drag increase altered trim calculations. Additional ballast blocks repositioned internally. Command procedures standardized across crews. Operational secrecy limited public acknowledgement. Mission reports stored under restricted classification. Engineering lessons influenced subsequent designs. Program effectiveness evaluated after major operations. Strategic reassessment reduced further procurement. Remaining hulls reassigned to training roles. Design documentation archived within Admiralty records. X-craft represented constrained engineering solution. Performance remained dependent on exact execution. Failure probability remained consistently significant. Operational success required cumulative precision.